Hello everyone. Today we are talking about the fundamental theorem of calculus. So the fundamental theorem of calculus has a short name, FTC. So that means we choose the first letter of each word. So the FTC was first discovered by Newton and Leibniz. So this is the version of FTC discovered by used by Newton. And in Newton's time, people use different notations. So they use fluent and flexion. And so this is the FTC, the Newton's version of FTC. You can see it's d over dt of fluent equal to flexion. And Newton draw a picture, geometric picture in his book. So this is an old version of the first part of FTC. So the fundamental theorem of calculus contains two parts. So that is, suppose f is continuous on a closed interval AB. So the first part tells us that if gx is such an integral, then gx prime equal to fx. And the second part tells us how to evaluate an integral. So we will focus on the first part of FTC in the beginning. So in the first part of FTC, we can see there's an integral. And this integral gx has a variable in the upper limit. And the first part of FTC is about the derivative of gx. You can see gx is such an integral. It's the derivative of gx as a function of x is equal to the value of ft at the point t equal to x. So we noted that part 1 can be rewritten as this formula, d over dt of that integral equal to fx. So you can see the process of integration could be inverted by the process of differentiation applied to gx. So the assumption is the function f should be integrated, and the result is differentiated, and then we can arrive back at the original function f. So you can see FTC is really important because it gives us the connection between differential calculus and integral calculus. So it is the cornerstone of modern calculus. Now let's go to the detail about the first part of FTC. You can see here the gx. So gx actually is a function of x. That is, when x is fixed, then gx is a definite number. When x vary, the gx is also vary. So gx is called an indefinite integral, by many others. So gx is an indefinite integral. Now, you may ask me how we can prove the first part of FTC. So now let us go to the detail about this formula. So here, a is a constant. But x is a variable. And the result is fx, and x is a new variable. So this part 1 of FTC was first proved by Leibniz. Leibniz used geometrical methods to prove the first part of FTC. And his proof is very intuitive and very easy. Now this is his proof in modern language. You can see, so this picture actually is just a reproduce of Leibniz picture. So you can see in this picture, so we can think of Gx as the area below the curve y equal to ft. So we try to represent Gx by a graph and the derivative Gx prime as the slope. So now look at this picture. So the difference Gx plus h minus Gx is what? Is simply the area, between x and x plus h. This difference for any h positive is the area, between x and x plus h. So this observation is very useful because, so what's the derivative? The derivative is just the quotient of the difference, right? The derivative, by definition, the derivative is the difference divided by h. Now, from the picture, geometrically speaking, the quotient, the difference quotient, is the rate of change of the area under the curve. So if h is very small, then the rate of change, of the area is equal to the height of the curve at the point x. So that means if h is very small, so the difference is almost h times fx. So the quotient is fx. Now if we let h go to 0, we can obtain that Gx prime is equal to fx. So in this way, you can see we can prove the first part of FTC. So this is the first part of FTC. It tells us that the indefinite integral Gx is an antiderivative of f. And from the basic of differential calculus, we know that for any antiderivative, if we add a constant c, then it is also an antiderivative. Because what? Because the derivative of c of any constant is 0. So we can add a constant to any indefinite integral. So generally speaking, the general form of antiderivative is formulated in this way. So this is the general form of antiderivative. Now let us go to the second part of FTC. So the second part of FTC, it tells us that if f is any antiderivative of, if the capital F is any antiderivative of f, then we can evaluate the integral of fx, by using the difference of capital F. So this is easy to prove. It is not hard to prove, by using the indefinite integral. So now this is what we want to prove. Okay, this is what we want to prove. And so that is because, this is the definition of an antiderivative. Any antiderivative is the indefinite integral plus a constant. So now we plug in x equal to a, so we can get this formula. And then we plug in x equal to b, then we can get the second part of FTC. second part of FTC. We can reformulate the second part of FTC like this, net change theorem. So this theorem tells us that this theorem is a most important rule for finding the integral between a and b. In other words, to evaluate the definite integral, we need only find a function fx such that we need to find a capital F such that the derivative of capital Fx is equal to Fx. And then we can form the difference Fb minus Fa. In this way, we can compute an integral. So you can see this formula is very powerful. So, if we now we look at this example, okay? So now let us compute this integral. Now we know that the antiderivative of sin x is minus cosine x. Now by using the second part of FTC, this is easy to compute, in this way. And then by using some high school algebra, we can compute the integral is 1. Okay, that's all.